Hey everyone, welcome back. This video will be about our Archimedes principle, which is kind of a natural progression from Pascal's principle. All right. In both, it deals with a stationary fluid. Okay, so nothing's moving. All of the hydrostatic pressures basically cancel out. Okay. But Archimedes specifically deals with why objects float. Okay, or in other words, it deals with where the buoyant force comes from. So in order to show you guys, I need an object that can be partially submerged in a fluid with the top and bottom surfaces the same, right? The area is equal and kind of horizontal. So I'm going to choose a cylinder. Actually, let's make that a little bit longer. Cylinder. There we go. All right, so this cylinder has a top area A and a bottom area A, and it's of length, or height, if you will, capital L. All right, and so this is partially submerged in a fluid. I'm going to draw something like that. Right, and so there is some height, right, that extends above into the air, and some height that extends below into the fluid. So that means above, it's basically the density of air, and below, it's the density of fluid. All right. So, one more thing to clarify before we actually start. This point down here will be some pressure P1, right? And I'm going to talk about the pressure at the boundary between air and fluid, right? So this is at pressure P2, right up here. I'm not going to deal with the difference in pressure between the very top and the surface. Compared to the difference in pressure between these two heights, this difference in pressure is very, very small. Okay? The actual height may be comparable, but the difference in pressure could be very small, right? And in fact, it is. So for this derivation, I'm only worried about the pressure at the fluid's surface and the pressure at the bottom of the object. Okay, so now let's look at the forces on this object. Well, it has its own inherent weight, right? So let's go from about the center of mass downwards. So I'm going to call this the mass of the cylinder times g, right? So that's the mass of the actual material plus all of the contents inside. And we have the force on the bottom pushing up, so that's F1, and the force on the top pushing down. Okay, notice the magnitudes of F1 and F2. F1 is larger than that of F2, okay? And that comes from Pascal's principle. Right? There's simply a change or difference in height. Thus, the forces and the pressures must be different. Okay? So, with that in mind, we can write out the net force equation. Let's see. I'm going to call up as positive as before, and so we get a pretty similar equation to the one in Pascal. That's the cylinder, by the way. All right. And now, Archimedes only deals with the difference between F1 and F2. Okay? This will come into play later at the end when we relate the difference in the forces to the weight of the actual object that's submerged. Okay? So for right now, I'm only dealing with that difference in force. Okay? So in order to do this, I need to write this force in terms of pressure and area. Well, P1 times A, that's the pressure at the bottom, minus P2A, right? Oh, by the way, these are a difference, we'll say H, okay? Not necessarily the same as the total length, right? For a partially submerged object, L and H will not be the same. All right, so pressure area minus pressure area. That's the same area, and I've chosen that on purpose, so we can kind of factor that out. All right. What's P1 minus P2? Yes, it's a positive value, but remembering back to Pascal's principle, a difference in pressure is equal to rho g times the change in height between those 2 points, 1 and 2, rho gh. And specifically, what's this density? Well, it's the density of the fluid between those 2 points, right? Actually, I should put, since both air and water is a fluid, this might not be the best nomenclature. We can put that as water. So that's the density of water times G times H. And then times the area. All right? And so this is known as the buoyant force. Right? It's still a force, right? The units still work out to be newtons, right? Kilograms, meters per second squared. However, it's just written in terms of, well, density G, H, and A, right? What's H and A? That's really a volume. So another way to write the buoyant force is the rho, right? The density of the fluid times G times V. And now let's look at this volume V. Specifically, that's the area times H. So really, that's the volume of the submerged object, right? Or that's the volume of the fluid that's displaced when the object is submerged, okay? It does not have anything to do with that volume up there that's in the air. So if you insert an object in a body of water, right, it floats because some portion of its total volume pushes away, literally pushes the fluid out of the way. And in this case, it's just this. And that's the same right there. So that's the buoyant force. And again, from up above, the mass of the cylinder times G. So we have two forces here. This difference is the same as the buoyant force, right there. And then, as before, we kind of took a break from it. Mass of the cylinder times G, that's the same as this force here. So the buoyant force is simply equal to the weight of the object itself. Okay, so we can write this rho g v equals, and if you want, we can write this in terms of, let's see, rho v as well, right? I'm going to put that as displaced. And putting mass in terms of density and volume, we have the density of the cylinder times the volume of the cylinder times G. If we write it this way, little g cancels out, and we simply have a ratio. However you want to write it. Density of the water, volume displaced. Actually, let's do it this way. We can write the volume displaced divided by the total volume is simply equal to the the density of the cylinder divided by the density of the water. So that means that we can find a percentage of the volume either outside the fluid, right, compared to the entire volume, and that's simply the ratio of the densities. All right, this will come into play on the next example, but this video here, the big thing was that the buoyant force was simply equal to rho GV of the fluid displaced. Okay? So there you go. Thanks for watching.